Let's look at 6.3a binomial distributions. So far we've just talked about probability distributions of random variables. So now we're going to go into a special type of distribution, which is called a binomial. So anytime you see the bi, like bicycle, there are two, okay? So we're going to talk about something dealing with two, so binomial. So here is some vocabulary. Binary, the possible outcomes of each trial can be classified as success or failure. Hence, two. We have success and we have failure. So you have to define what success means and what failure means. So an example would be like rolling an even on a pair or on one die. So there has to be a clear success and failure. So success would be rolling an even. Failure would be rolling a not even, or, not even would be odd. Okay, the next thing that we need to check for binomial settings is trials must be independent. That is, knowing the result of one trial must not tell us anything about the result of any other trial. So they are independent. Number. The number of trials in of the chance process must be fixed in advance. So rolling the die 20 times. So as long as that is set in stone in the very beginning, that's what you want. And then there's the same probability P of success in each trial. So the probability of rolling an even would be 1 out of 6. No, 3 out of 6, which is 1/2. Okay, so in order to check the conditions for binomial settings, you're going to check your BINS, B-I-N-S. So binary, success and failure, I for independent, N for fixed number of trials, and S for same probability for each trial. The count X of successes in a binomial setting is a binomial random variable. The probability distribution of X is a binomial distribution with parameters N and P. Okay, and N is our number of trials of, not or, number of trials, and P is the probability of success. So let's say 20 trials, probability success is 1/2 on any one trial. The possible values of X are the whole numbers from 0 to N. So if we have 20 trials, we would look at how many result in success, which success was our even. So what are the most common mistakes for students on binomial distribution questions? Students not recognizing its binomial setting and just applying normal distribution. And it is one of the most commonly missed test items. So we are going to spend some time on this, make sure you got it down. So here's an example. Determine whether the random variables below have a binary distribution. Justify your answer. So here's our example. Roll a fair die 10 times and let X be the number of sixes. So we need to check our BINS. B, success. What is success? Well, it says getting a 6. Failure means not a 6. I stands for independence. One roll of the die does not affect the next, so it is independent. N. How many times did it say we were going to do these trials? It said 10, so rolling the die 10 times. And S. Probability of rolling a 6 is 1 out of 6 each time you roll the die. So it is a probability distribution. We checked our BINS. Let's go to the next one. Shoot a basketball 20 times from various distances on the court. Let Y be the number of shots made. So let's check our BINS. BIN for B. Success, shots made. Failure, shots missed. So there is clear success, clear failure. I, Independent. Does making one shot affect the next? No. One shot does not affect the next. So it is independent. In. How many trials? It says 20. So shooting 20 times. And S. Probability of making a shot is 1/2 each time you shoot. You either make it or you don't. Unless you have someone specific percentage of shots that they make. We did a simulation one time where we were looking at someone's shots that they made, and they gave us how much their probability was. But otherwise, we're just going to use 1/2. So this is a binary distribution. All right, let's go to the next one. Observe whether the random variable shows binary distribution. So observe the next 100 cars that go by. And let C equal color. Okay. B is a success and failure. It says color, but it doesn't say what color. Since there are more than one color possibilities, this is not a binary situation. So this is not binary setting. So once you see that one of the bins, one of the acronyms, one of the letters doesn't work, you can say it is not binary. If they would have said, let C equal the color of blue cars, then that would be different. And then they would tell you how many the probability of, or what the probability of having a blue car is. Okay, the next one, it says, in many games involving dice, rolling a 6 is desirable. The probability of rolling a 6 when rolling a fair die is 1/6. If X equals the number of sixes in 4 rolls of a fair die, then X is a binomial with N equals 4 and P equals 1/6. So N is our number of trials, so it's 4 trials. P is the probability of getting a 6, which is 1 out of 6. What is probability of X equals 0? That is, what is the probability that all 4 rolls are not 6s? So we're saying that the number of successes is 0. So that means probability of X equals 0 is probability of all failures, which, remember, failure is not a 6. So these are all not 6. So we would do multiplication of these probabilities because they're all independent, remember? So 5/6 is probability of not getting a 6. So probability of failure is 5/6. So 5/6 times itself 4 times for 4 rolls. So we can write that as 5/6 to the 4th power, which is 0.482. Okay, now let's look at when we get X equals 1. So X equals 1 means you got 1/6. So probability of X equals 1 is probability of a success and then failure, failure, failure. So then we'd multiply it 1/6 times 5/6, 5/6, 5/6. So here's our values that we're going to multiply. 1/6 times 5/6 to the 3rd. But are there different ways that you could roll 1/6? Yes. We could do failure, success, failure, failure. But it would still be the same value. 1/6 times 5/6 to the 3rd. So what other options? Failure, failure, success, failure. Still the same thing, though. And then one more. Failure, 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 success. So there's our failures. There's our success, which is the same thing. So we do need to add each of these up. So instead of saying this plus this plus this plus this, they're all the same thing. We could do 4 times 1/6 times 5/6 to the 3rd. Because there are 4 outcomes for getting 1/6, rolling 1/6. Here are the 4 outcomes, 4 possible events. So 0.386. Okay, we don't want to write this every time, but we've got to find the pattern. So let's see how we can do that. Okay, so we want to do probability at X equals 2, X equals 3, and X equals 4. So X equals 2, there are 6 possible outcomes. I'm going to show you how to calculate that. But you would have 1/6 to the second because that's your 2 successes. And that means you have 2 failures. You get 0.16 because you have to do the 6 times this. We could list out all the ways that you can get 2 successes, kind of like what we did a minute ago when we wrote all of these down. But I'm going to show you how to use a calculator to do that. In Desmos, you can do the same thing. All right, so probability that x equals 3. There are 4 possible outcomes. And so we do 1/6 to the third, 5/6 to the first, which gives us this probability. And then probability x equals 4. Well, there's only one way that we get 4 successes. So we would only need this once. 1/6 to the fourth, 5/6 to the 0. Okay, so number arrangement, see these highlighted in yellow, is called our binomial coefficient. What that represents is how many ways can you get that outcome of 2 successes, of 3 successes, of 4 successes. So that means that of getting 2 successes, there's 6 outcomes. 3 successes, there's 4 outcomes. 4 successes, 1 outcome. So the way we do that is this. Okay, so this is saying N choose K. See how there's no line here, so it's not division. It's not a fraction. So the way we do that is this is the formula. So N over K is N factorial over K factorial times N minus K factorial. There's punctuation in our fraction now. So factorial just represents something times itself over, well, something times the next number. So it's like, if this is 10, it'd be 10 times 9 times 8 times 7 times 6 and so on. But we can just use our calculator for this. It's called a combination. NCR. So we do 4, choose 2. In general, how can we calculate those binomial properties? So we would need to do this first to figure out what our binomial coefficient is. And then we would do, we would find out how many outcomes there are. And this would be our equation. So N choose K, P to the K, because that would be how many outcomes you actually got. So like 2 or whatever. And then 1 minus P, which is the not P, N minus K. Let me go back to that. So that is the formula we will use. Okay, let's look at the next problem. Oh, and by the way, that formula is on our chart, so you don't have to memorize that. Okay, in roulette, 18 out of 38 spaces on the wheel are black. Suppose you observe the next 10 spins of a roulette wheel. What is the probability that exactly 4 of the spins land on black? So first thing we need to do is check the bins. So B, do we have success and failure? So success is black. Failure is not black. Let's see, what's the next one? I, independent. Is each spin of the wheel independent? Yes. N, how many times are we going to spin it? 10. So we're good. S, probability of making it, probability of success, so that'd be 18 out of 38. So that's clear. So good, it's binomial. All right, so here is for exactly 4 spins. So we use that formula. So it's P, X equals 4. Exactly 4 spins are going to land on black. We're going to do 10, choose 4. And then this 18 out of 38 comes from how many are black? 18 out of 38 to the 4th, because I want to get 4 of those. So then I need to find not black. So it'd be 20 out of 38 because you subtract. And that's to the 6th power because we're doing 10 spins. So this exponent and this exponent should add up to be 10. We can put this straight into the calculator and get 0.225. So there's approximately 22.5% chance of landing on a black 4 times out of the 10 spins. So you will have to write each of these things. Context, how many times you want the success to be out of how many total spins or in trials. Okay, one last one. What's probably that at least 8 of the spins land on black? So at least 8. So that means it's 8, 9, 10, right? So we're going to have to find each one of these and then add them together. So you'll need to do this formula 3 times and add them together. So here's for x equals 8. Here's for x equals 9. Here's for x equals 10. And so we would want to add those up, and we get 0.43. So in words, we would write the probability of at least 8 spins landing on black is about 43% when there are 10 trials. All right, that is it.